Hello and welcome back to chapter 4. We are just finishing up talking about cycloalkanes, and in particular, we're going to talk a lot about cyclohexane. But before we get to that, let's go ahead and review the types of cycloalkanes that we can actually see this semester. So remember, in a cycloalkane, alkanes are all sp3 hybridized carbons, so they should be tetrahedral. They should have bond angles of 109.5 degrees. If each cycloalkane were flat, then each carbon in a given ring would have to have some kind of angle strain, kind of pulling it closer together. Basically, it's taking the angles, the bond angles from what they should be, 109.5, squeezing them in or widening them out. So you can just go to the simple geometric shapes, and sure enough, this is what we draw when we're drawing stuff on your sheet of paper, on the computer. Cyclopropane, for example, looks like a triangle, and you can say pretty surely that bond angle is about 60 degrees. And then from there you move up, cyclobutane we draw as a square, cyclopentane we draw as a pentagon, cyclohexane is a hexagon, heptagon, octagon, etc. Yeah, so not only that, if the ring was flat, then if you did the Newman projections, you would see, oh, everything's going to be in an eclipsed rotamer. And that's not good, right? We just learned that in the last one, where the eclipsed rotamer is the least stable conformer. So that means that's no good. But of course, you probably already figured this out. These molecules operate in 3 dimensions, just like you and me, right? So most of these cycloalkanes aren't going to be limited to the 2-dimensional thing. What's going to happen is instead, they're going to bend and kind of like morph into 3 dimensions to reduce the angle strain and the torsional strain. And if you check out, you can actually calculate the heat of combustion per CH2 group. This is kind of our proxy for how stable a cycloalkane is going to be. And the reason we have to do that is, of course, as you add more CH2 groups to it, you're going to increase the heat of combustion overall. So just we normalize it to the fact that each carbon in the cycloalkane is going to be a CH2. So just divide it by the number of those. So cyclopropane, we take its heat of combustion, divided by 3, that gives us 697 kilojoules per mole. Cyclobutane comes in at 680 kilojoules per mole. Cyclopentane down to 658. Cyclohexane, that's our minimum, that's at 653. And then from there, we go up to cycloheptane at about 657, and we only kind of moderately increase until we hit, say, like cycloundecane at 661. So we notice right away that really like the minimum is going to be cyclohexane. And this indicates that because the heat of combustion is the smallest, that cyclohexane must be the most stable for some reason. And we're going to go over those reasons here at the end of this chapter. So first up, we mentioned that these shapes kind of deform from what we draw on the page, so that they kind of reduce that angle strain and reduce the torsional strain as much as possible. So starting with cyclobutane, now cyclopropane, there's no flexibility. It's just those 3 carbons are in a triangle. There's nothing you can do to flex out of that. But with cyclobutane, there is a little bit of give to the cyclobutane. What happens is rather than a square, you get this sort of puckered conformation is what we say. So it sort of like goes from a flat square like that to like a puckered form like that. And this changes the bond angles from what they would be to 88 degrees. So there is quite a bit of angle strain, but because of this puckering, you can actually reduce the amount of torsional strain. So no longer do you have like a direct eclipse like you would in a square conformation if it were just a fully flat square. Yeah, so something to keep in mind, and you can kind of see that as you look at that here. Now, we're not going to focus too much on cyclobutane. Again, it's not the most important molecule compared to what we're about to talk about, cyclopentane and then cyclohexane. So just know it's like it is just trying to get out of the worst torsional strain that it can. Okay, cyclopentane, on the other hand, as you would expect, a pentagon has internal angles of, I think, 120 degrees. So with just a little bit of bending here and there, you can actually have a reasonable, very close to 109.5 degree arrangement of these carbon atoms. And so cyclopentane, very stable. And it's a pretty common ring that we see a lot in organic chemistry. Now there is a little bit of torsional strain. That's because you can't quite totally get away from, you can't get into like the perfectly staggered formation. So it gets as close as it can to a staggered formation, but it's still just a little bit off from that. So you get a little bit of that torsional strain as you're looking at the Newman projection of it. Now, cyclohexane is the most stable, and because basically the reason that it's the most stable is pure geometry. The carbons, you can think of them as like they're points, and they have certain principles. And the thing that it needs to satisfy is it needs to have 4 bonds. It's going to be bonded to 2 carbons that are next to it, and then after that, it is going to be bonded to 2 hydrogens as well. And the bond angle should be as close as they can to 109.5. So now there's multiple conformations possible. At this point, I recommend just go ahead, pause the video, and build a little cyclohexane molecule. And we're going to kind of like look at some of those conformations now. The most stable one is what's called the chair, which sort of looks like this. I'm going to rotate it around like so. Again, if you have a nicer kit, you're actually going to get a better feel for what the chair should look like. But it looks something like this. You see there's like a little leg rest down here. This is where you lean back in the chair, and then this is the seat here. Now, these can twist, and they can form like a half chair, for example, something like that. And then they can twist into a boat, and then they form the boat. The boat's the least stable conformer. We're not going to really look at the boat too much, but the boat basically is like this, where it's like you can imagine both of the chair backs are up there. And as you can see, it's not very stable. And the reason that it's not very stable, even though the torsional strain has been reduced, you have a lot of conflict between these 2 substituents here, which happen to just be hydrogen in this case. And then what can happen is if you flip it the rest of the way, you can actually flip into the opposite chair. We'll talk about this more in a little bit, but just these conformations can kind of flip from one to the other. Okay, so looking at the chair conformation in particular. So again, I hope you have a model kit. Just try to build one of these chair conformations. The angle strain, perfect. It's almost exactly 109.5 degrees for all of these carbon, these bond angles in the carbons. Additionally, the torsional strain is really good too. Now, this is a skill that we're going to have to practice, but one way that you can draw a cyclohexane is by drawing it as a connected series of two Newman projections. So here, hold on. This is a really cheap model, so it's not working with me very well, but I think we can see it right here. So what you can see is here we've got a front and back on the left side, and as you can see, we have staggered conformation of the substituents behind it. And then if we look at the other side, sure enough, it's another front back, and the substituents on that also look quite staggered. So we've eliminated basically all the torsional strain, and just geometrically speaking, it worked out perfectly. The angles are at about 109.5 degrees. So yeah, so we looked at the other conformations on the previous, and we saw, oh, there's a bit of strain here, especially when it's going into like chair or boat chair conformation. So I'm sorry, into boat or boat chair conformation. So we know that like at its most stable, the cyclohexane is going to be in the chair conformation like this. Okay, so how do you draw a chair conformation? So basically what we want is we want to draw this little like, it's like a hexagon in a way. I guess it's a type of hexagon, but it's not one of the platonic structures or whatever. Instead, what it is it's kind of a 3-dimensional representation of what this chair should look like. So here, we'll do it together. I'm going to go ahead and I'm going to use my straight drawing line. So what you're going to do first is draw a wide V, something like that. And then from that wide V on the right side, draw a line going down at about 60 degrees. So something like that. And it should go a little farther, maybe right there is good. doesn't have to be perfect. Obviously, you've seen me draw on these things. You know that I'm not perfect at it. This is just going to give us a good representation of what this chair formation conformation is going to look like. Okay, then what you're going to do is draw a line parallel to your first line. So it looks something like that. And it's going to stop just short of where it was before. Now you're going to draw another line here that's parallel to this line over here. And lastly, you're just going to connect the last two dots that are there, which looks like that. And that's your chair. Again, it's not perfect, but you do your best, and that's good enough anyway. That's our way of representing this chair here. So kind of try to match up your drawing there to what the chair looks like. Again, just looking at the carbons for now, but you can kind of see how that works. I'll get some practice on it. Okay. Yeah, so if you drew it properly, you should see basically three sets of parallel lines where on opposite sides, those are parallel. Your first line is parallel to this line down here, and then the last line that you drew in was parallel to the second line that you drew over here. Now, one thing that's interesting, and you'll see this if you build your model, as you look around here, there's two different substituents on each carbon, right? And these are all hydrogens for now, because this is just pure cyclohexane. But what you notice is each carbon is going to have a hydrogen or a substituent that's sticking either directly up or pointing directly down. So like, for example, this carbon here, this carbon has this hydrogen sticking straight up, and that skips. So this one skips, and then this one has one pointing straight up. This one has one pointing straight up. Then look at the bottom. The carbon that was next to the first one we looked at, that has a hydrogen that's pointing straight down, like that. So because these are on basically the z-axis, as we're looking at this molecule, we think of these as axial substituents. And that's an axial position on this cyclohexane molecule. Now, also as you go around, you notice the other one. The other ones are like sticking out. And you can notice, based on this first one that we saw, we have the axial one pointing up. We have this other one kind of pointing out and down. Looking at its neighbor, this one had its axial substituent pointing down. This one is pointing up very slightly, but mostly out. So this is what we call the equatorial position. So each of these carbons has an axial and an equatorial position that it's got bonded to it. Try to look around and see and identify these axial and equatorial positions as you go around your model here. So axial, equatorial, and down. So again, notice we have axial is pointing up. That means equatorial is out and down. Here, the axial is pointing straight down, and the equatorial is up and out, mostly out. So give that a try. Go around your ring and see if you identify where those positions are. Okay, so now if you're drawing where these axial substituents are, it's actually pretty easy from your chair model that you drew before. So here, I'll draw another one. Hopefully I won't embarrass myself too much here. Again, you do a wide V, like so, down at 60 degrees, parallel to your first line, down and down. Good enough again. And now drawing in the substituents. So our axial ones, note here, this carbon, it's pointing up. So this is a model of my chair conformation. This one right here, that's analogous to this one right here. We notice that its axial is pointing up. Well, if this one's pointing up, that means that this one, as it's the neighbor, that's got a slight depression there, it's dipping down. So that means its axial is going to be pointing down. We alternate up, down, up, down, up, and down. And those are our axial substituents. So it's pretty easy because you can just identify, oh, they're going straight up and straight out. What's a little harder is actually drawing the equatorial ones. So here, I think if I can bring up the next mark here. Your equatorial ones are a little bit harder to draw, but again, once you have your model here, it should be pretty straightforward. We're gonna change the color here now so we can kind of see what's going on. So the equatorial ones are pointing kind of, they're pointing the opposite direction of the axial. So this axial is pointing up. That means that our equatorial has to point out and down. So out and down like that. On this one, the axial is pointing straight down. So the equatorial is going to be up and out like so. Similar here, our axial is pointing straight up. So the equatorial has to be out and down, out and up, out and down, and out and up, like so. And that should give you a kind of a good idea of what how you're going to draw these cyclohexane rings from here on out. So give it some practice and see how you do with that. Okay. Now, what's interesting is, and here what I'm going to do is I'm going to replace one of these hydrogens with just a nitrogen here, a blue one here, so we can kind of see. So if you have just a mono-substituted cyclohexane, you just have one substituent, like what we have with the nitrogen here. Imagine it's a chlorine or something like that. In this chair conformation, we notice that the nitrogen is in an axial position, so it's pointed straight up. But we already mentioned that this can flip from one of two chair conformations. So it could be like this, or flip it the other way. Again, this model kit is the worst to do this with, but I will do it with you here. Okay, and now we flipped it. I didn't break any bonds. I didn't move anything around. I just flipped it. And we found our new chair conformation. And all of a sudden now you notice, while the nitrogen is still pointing up very slightly, it is now pointing out mostly. So now it's in an equatorial position. So you can flip from the axial to the equatorial position. Okay, so here we have the equatorial position here, and it can flip again to going into the axial position. Now, if we consider methyl cyclohexane, so that's just where you have a methyl group here, where this blue molecule is. If you actually look at a sample of methyl cyclohexane, the most of the cyclohexane molecules that you're going to have at equilibrium, you're going to have about 95% of the equatorial methyl group. So the methyl group is going to be in the equatorial mode about 95% of the time. And again, you know, they're flipping back and forth. You're not going to isolate one from the other. It's an equilibrium process. But this is telling us something, that at equilibrium, we have a preponderance of the equatorial substituted group. So that must be the more stable version. So if you have a mono-substituted cyclohexane, the equatorial is going to be the more stable. Now, the reason for that is because if it's in the axial position, there's actually going to be a lot of steric interactions that we have to consider. And again, this is where we're going to go back to our Newman projections. And in particular, we're going to look at Newman projections of cyclohexane molecules. So, starting from the axial position. Okay, so if we have so let's put our methyl group in the axial substituent here. Once I get it in the chair mode again, I'm going to show you again. Great, okay, cool. You can just kind of make it happen. So it's axial there. Now the way we want to look at this is just look at, we can draw a kind of special Newman projection, as I mentioned already, by actually looking at basically two Newman projections at the same time. So we have our front carbon down here. That's the closest carbon to us, but that's not really what we're looking at. We're actually looking at the two side carbons here. We have basically a Newman projection here and a Newman projection here. And we know that we can do that because, remember, like a Newman projection, you're looking down a bond axis. Well, these axes are parallel, so you can look down both of them at the same time. And sure enough, that's what we're going to do. So what do we notice as we look at this? Well, this methyl group is going to be gauche to this back here, which is our connecting CH2 group. That's a pretty, this is taking up a lot of space back here. And so that is not a favorable interaction. There's a significant amount of torsional strain from that. If you flip it, on the other hand, so that again, this is our nitrogen here, but we can think of it as a methyl group, like what we say on the slide. So flip it. There we go. Okay. Okay, so we flipped it now, and we're going to look at that straight on. Now all of a sudden, this is staggered, and it's actually anti the CH2 connector on the other side. So you're not having a negative interaction there at all with that methyl group. So the more it sticks out in the equatorial position, the less torsional strain you're going to get from this methyl group or from whatever substituent you have. It's true for all of these monosubstituted cyclohexanes. And so you can go for like, you can have these 1,3 diaxial interactions. This is what causes, this is kind of like the hydrogen-hydrogen gauche interactions or the hydrogen-hydrogen. Yeah, these were the gauche interactions that we were talking about, but this time, rather than talking about a hydrogen or a methyl group, we're specifically talking about with the CH2 in the back. So that's like this thing back here. So if it's a chlorine, that costs about 2.0 kilojoules per mole to be gauche. For a hydroxyl group or an alcohol, that's 4.2 kilojoules per mole, methyl group 7.6. And then anything bigger than that, as you can see, it gets more and more expensive, a bigger and bigger steric cost to do it. And what happens is basically with the chlorine, you get a 70 to 30 mix of the equatorial to axial substituent at equilibrium. And as this cost goes up, you get less and less and less of that axial substituent. When you get to a tert-butyl substituted cyclohexane, it's actually about 10,000 to 1 that you have the equatorial versus the axial. So it doesn't spend much time in the axial position at all. Okay, so that is for monosubstituted cyclohexane. But you can also imagine a disubstituted cyclohexane here. So let's go ahead. I'm going to actually build the molecule here for you. We're going to have chlorine. Chlorine is going to be the green atom here. And then the methyl group, again, just like before, I'm just going to substitute the methyl group with one of the black carbons here so that I don't have to build the CH3s on it. We can just know that this is a stand-in for a methyl group. So in this case, we see here, chlorine is pointing up and its neighbor, the methyl group, is pointing down. So, okay, so I'm going to flip this. So we have a methyl group pointed down. That's this one here. I can even like put it in position here like this. So making it look to you like it's coming into the screen would look like that, right? It's coming into the screen towards me. Now its neighbor, the chlorine, is pointed up. So we go to its neighbor, which is going to be this one here. And sure enough, it's going to point out at you. So let's go ahead and substitute that hydrogen in, like so. So again, the methyl group pointed into the screen towards me. The chlorine pointed out of the screen towards you. Okay, so now we actually have two possibilities here. We have this one here, where the methyl and the chlorine are both equatorial, and we can flip it, right? So let's flip it and get our other chair conformation. Like that. And now we see the methyl group is axial pointing down and the chlorine is axial pointing down. Yeah, sorry, methyl is pointing down, chlorine is axial pointing up. Okay, so that's the two possibilities there. Now, why don't you go ahead and work on this here using ethyl and methyl at like a 1 and a 3 position here on the cyclohexane. Draw the chair conformation and then flip it. So flip it and show what that's going to look like after you do that. So we'll do the chair conformation looking something like this. So, so first up, what you do is just go ahead, draw the chair conformation like what you did before. Now you're going to say, okay, ethyl is at carbon 1, and just pick a carbon to be your carbon 1. I just always choose this rightmost carbon to be my carbon 1. And we know the ethyl is pointing up. And so on this one, we know that the ethyl must be an axial position on carbon 1. So then we go to carbon 2 and then carbon 3. So carbon 3 is kind of opposite. And now we have the methyl group pointing down. Well, the axial points up, so the equatorial must point out and down on carbon 3 here. So that's our first one. Then what we can do is we can imagine flipping it. And when we flip it, what happens is you basically just reverse the symbol. So now carbon 1 had ethyl as its up axial and hydrogen as its down equatorial. When it flips, now the hydrogen is going to be pointed down in the axial position. Ethyl is going to be pointing out in the equatorial position, and vice versa, whereas methyl group was pointing down in the equatorial. Now, when it flips, it's pointing down in the axial direction. So those are our two possible conformations. We can either have the ethyl as an axial and the methyl as an equatorial, or we could have the methyl as an axial and the ethyl as an equatorial. Okay, so which one is going to be more stable and why? Go ahead, pause the video, reason it out, go back over what we talked about with monosubstituted cyclohexanes, and hopefully that will tell you what the answer is. So pause. Oh, I thought the answer was on the next slide, but we can just talk about it here. So the more stable conformation is going to be the one that reduces that gauche interaction, right? So if you have to choose between reducing the interaction between an ethyl group or a methyl group, well, an ethyl group is much bigger than a methyl group. So the ethyl group is going to dominate. So you would say that the chair that has the ethyl group in the equatorial position is going to be more stable. Likewise, if you had to choose between, for example, if we go back to our chlorine and methyl group example here, if you had to choose here, you have chlorine and methyl in in axial positions. Those are going to have a lot of 1,3 diaxial strain. So it's going to be much more stable in the in this position here where they're both equatorial. So that's going to be much preferred and much more stable. I do realize that does bring in a gauche interaction here, but that gauche interaction is much less than what it costs to be gauche to your diaxial position on the back. Okay, so now we can also want to bring up trans stereoisomerism. So this is going to come up more in the next chapter, chapter 5, but you can actually name a cycloalkane cis or trans based on if it has two substituents. Are they on the same side of the ring? Are they pointed up or pointed down? Or are they on opposite sides of the ring? So are they pointed opposite ways? So up, down, or down, up. And so cis is like Latin for same. So when both substituents are pointed the same way, so up or down, then that's a cis cyclohexane or a cycloalkane. And when they're pointed opposite ways, we use the word or the prefix trans. So for example, here we have 1,2-dimethyl cyclohexane. If both methyl groups are pointed up, that's a cis 1,2-dimethyl cyclohexane. Whereas if they're pointed opposite sides, now it's trans 1,2-dimethyl cyclohexane. And this brings up this first word here. These are what we call stereoisomers. They have basically, everything would tell you that they're the same, right? They have the same molecular formula. They even have the same bonding, but that bonding is oriented differently in three-dimensional space as what we just saw here. So they are, this is the first type of molecule that fits this stereoisomerism, and that's going to be what the whole next chapter is about. Yeah, so for example, because you have these different, I already mentioned they're different, right? They have different connectivity in 3 dimensions. So what that means is you have basically 2 different sets of chairs where you can have here axial equatorial, here you can have axial axial or equatorial equatorial. You just have to kind of be aware of that as you're drawing your chairs and making sure that you're understanding, you know, are they both pointing up? Are they both pointing down? Are they pointing opposite directions? Just keep track of that when you're drawing your chair conformations. Okay, this is just kind of cleaning up the end of this chapter, which is polycyclic systems. There's decalin, which can come up every so often in biological chemistry, especially in steroids. You can have a cis-decalin or a trans-decalin. This isn't going to come up much until we talk about lipids in the next semester, so don't worry too much about it. But these polycyclic systems, you can understand, like, it's basically when 2 carbons are members of multiple different rings, and that's the case here. There's also some really other interesting ones. So there's like norbornane, camphor, and camphene. Camphor you may recognize from insect repellent. It has a particular smell. If we were working in lab, we'd actually be working with camphor this year. And yeah, it smells like evergreen trees. So it's like a really pleasant camping smell, I guess you would say. And then really interestingly, diamond is basically a fused network of 6-membered rings is how you can look at it. And it's basically, you have carbons at each of these here. It's been fused after, a tremendous amount of pressure and a tremendous amount of heat gets applied, and that fuses into diamond. Okay, and that's where we're going to end it for cyclohexanes. So give it some practice. We have the lecture exercise down below this video. I'm going to be posting the video walking through that. I have my my document camera up and running now, so we're going to post that as soon as possible. And make sure to ask questions in the comments below. All right, see you around.